is Kim Seong-Jin. His on-site contributed talk, which will be 12 minutes for talk part and 3 minutes for Q&A. He is going to talk about energy duration relation of non-repeating CHIME FRBs. So, Seong-Jin, please try to start when you get ready. Okay, so it's working now.
Do you guys hear me?
Seong-Jin, please start.
Okay, thank you so much. So, hi, my name is Seong-Jin Kim from National Tsinghua University. Today I'm going to talk about duration-energy relation of non-repeating FRBs, which we call Hashimoto relation, based on the CHIME FRB data. So, so this work was published in the MNRAS and these are co-authors of this paper. So what is this relation? What is Hashimoto relation? Let me explain this first. So, yeah. So in one of our previous works, Tetsuya noticed for the first time that there seems to be a relation between duration and intrinsic radio brightness, which looks like this. It looks like a linear relation. And this relation is based on the publicly available catalog by Petrov et al. And this catalog compiled 68 FRBs in total. So, yeah, y-axis is duration and x-axis is intrinsic radio energy, and relation looks like this, linear. So it's really interesting because, yeah, if this relation is true, then we might be able to obtain intrinsic brightness just by measuring burst duration, which means a simple observation can directly give you the intrinsic radioluminosity. So it's simple and interesting. Yeah. Of course, in order to establish this relation, there are so many things to do first. Maybe revealing the physical origin could be the first one. But if this relation could be confirmed in the near future, the non-repeating FRBs could be used as one of the distance measure, can be an alternative distance measure. And this relation is kind of the brighter and the longer is going to sustain. So it's easy to understand. But in this relation, we are only talking about the non-repeating FRBs. And actually, this is a story about near future. So if you're going to have a sufficient number of samples in the near future, then we might be able to standard calibrate these non-repeating FRBs. So this could be kind of standard candle in the near future. And when the localization and spexy, this kind of things possible in the near future. And when we estimate the distance from the radio luminosity, then which can give distance modulus. And this distance modulus can be described as a function of redshift. So then we might be able, because this is kind of a Hubble diagram, so we might be able to have a constraint on the dark energy of the universe as a function of redshift. This is kind of just a simple summary of this relation, and this shows why it's interesting and why this Hashimoto relation is important. And yeah, this is the key point they wanted to say in this paper. But we have some problem here because this previous work used only a small number of sources, only 68 sources. But they had to reduce the number of sources down to 27 in order to use robust sample because they wanted more reliable analysis. Because of this kind of selection or truncation of the source, they worried that selection bias might exist, and also these 68 sources are heterogeneous. And also, as we know, there could be some possible contamination by potential repeaters. So if non-repeaters flashes again someday, then this non-repeater is not non-repeater anymore. So this kind of potential repeaters could probably be mixed or included in the one-off event sample, so this is not good. So we want to test a larger number of samples, and we want to avoid this kind of problems, selection bias, and possible contaminations by potential repeaters. So we used this kind of method. So in 2021, a new CHIME catalog was released, which has 536 FRBs, including 18 previously known repeaters. And this catalog contains various parameters for each subburst. And most of them are non-repeaters, and small number, 261, were identified as repeating types. So the number of samples used in this previous work is much smaller than this one. So we are wondering if, we want to know if this Hashimoto relation is going to be changed or significantly changed or not if we test all available CHIME FRBs. And I'm going to have to introduce another previous works about FRB classification. So after this CHIME catalog was released, Oliver, one of our students sitting over there, tried unsupervised machine learning method to classify CHIME FRBs, and found out that about 40% of the non-repeating FRBs are different from the other non-repeaters. So 188 non-repeaters out of 474. So this machine learning method used actually 13 parameters in total from the CHIME FRB catalog, but eventually reduced the number of dimensions and projected the results on this 2D plane. So this is the results of the machine learning method. And you can see many dots here, which are CHIME FRBs. And gray dots are non-repeating FRBs, and cyan and magenta dot is repeating FRBs. But so the most important parameters in this figure is distance to each other, because the sources which have similar characteristics are supposed to stay close together, forming cluster like this. So the thing is that CHIME FRBs were divided into several groups like this, and some of the non-repeaters here mixed with the CHIME non-repeating FRBs. So these non-repeating FRBs want to stay close to repeaters. So it's weird. So finally, eventually we decided to call them repeating candidates. So if we exclude real repeaters and repeater candidates, then this might be one of the best ways to avoid possible contamination from repeater or repeater candidates. So we have 286 number of the blue dots here. So what is better now? So now we can use 4 times larger number. And these numbers are homogeneous because all these FRBs are observed by the same telescope. And yeah, this 68 FRBs used in the previous work are actually heterogeneous because this color was just compiled the various FRBs observed from different telescopes. So the good thing is we are using homogeneous FRBs and 4 times larger sample. So, and we examined to see if there is really exist a linear relation. So this is our results, and the distribution of CHIME FRBs in the duration and its plane. So, so we obtained correlation coefficients, which are kind of indicator showing how strong the relation is, and with the significant values. So, so these are non-repeater at the redshift lower than 0.3, and so indicated by these blue squares, and the positive linear relation between the radio energy and duration seems to exist. So, so if the coefficient is 0, there is no relation, and if it's 1, then that means they have a tight correlation. So the correlation is going to be between 0 and 1. So the significance, for the significant 0.05 is kind of criterion. So only when the number is smaller than 0.05, the coefficient is statistically significant. So here the correlation is not very strong.
It's left.
Yeah, statistically significant. So these are repeaters, and this shows why we are trying to exclude the repeater samples. So it's totally different distribution. And these are non-repeaters at the higher redshift, and the slope changes and the correlation coefficients become smaller, and it's really statistically insignificant. So this is a summary. So we tested a much larger number, and we actually tried to exclude potential repeaters based on the machine learning classification. And actually, only the sample at the redshift range between 0 and 0.3 shows positive correlation. This is, even though it's statistically, even though the correlation is not very strong, but it's statistically significant, so it's undeniable. So about higher sample, but because the number of low luminosity sample is not enough, it's not easy to make a clear conclusion. So we still need more samples. So that's all. Thank you.
Okay, thank you very much. We can take 2 quick questions. So, do you have any questions from on-site people? Or online? Yes. He's maybe class.
You're referring to me and Kara? Yes. Thank you for this interesting talk, although I would like to know a little bit more about the correlation analysis on the second to last slide. But I was going to ask, a well-known effect is that wider FRBs are more difficult to detect because for a given amount of energy, you spread it over a wider time. You have a higher threshold. Have you accounted for this effect in your analysis? Because you would naturally expect low energy wide FRBs to have a bias against them and be less likely to be detected. And I know that CHIME, for instance, have done this very complex analysis using pulse injections to measure this bias. And so my question would be, are you sure that you're not measuring the response of the instrument as opposed to the intrinsic FRB population?
Can you summarize again your question?
My comment, comment then question. Comment, what the FRBs are more difficult to detect, and therefore the low energy wide FRBs should be missing from your sample? And question, have you accounted for this bias effect from the instrument in your analysis?
Yeah, so actually, when we realized that this source is kind of affected by this kind of biases, actually, that's why we're trying to estimate the Kendall-Stowe rank coefficient, which is more useful when we estimate this kind of numbers.
Sorry, can I? Sorry, interrupting. So can I add a little bit? So as far as I understand, in Seong-Jin's paper, probably we didn't really quantitatively check this observational bias for CHIME sample. So therefore, I think we have to carefully check in future. But in our previous paper, actually, we did a very simple multi-cloud simulation to test how much this detection bias affects the possible this correlation. And then it's changed the coefficient very little. It's smaller than what we found at the time. So therefore, I would say for the previous paper, we concluded that the detection threshold probably didn't affect very much. But for CHIME sample, I think you are right, and then I think it's a very important point. So maybe we need to be careful about this observation bias. Thank you very much for your question and comment.
Thank you very much.
Okay, and then if you're okay with this, and then sorry, I'm sorry. So time is out. So I think we have to close the afternoon session, and then let's thank the speaker again. Okay, so on